the last video. I said that it doesn't matter what path you take when you calculate the work done by gravity, and that's why you can make it a gravitational potential energy, a change in gravitational potential energy. So I'm gonna put my money where my mouth is. No, I'm just gonna do it. Okay. So I did the simple case of moving in like a rectangular path, and it's easy to calculate the work is 0 along some of those segments. But what if you do something more complicated? So let's look at this. So here I start up here, position 1, and I could go straight down and calculate the change in potential. That's easy. But what if I go along this circular path? Now, you can do this. You can do this analytically. You'd have to do some calculus, and I don't know if you're ready for that, but I'm going to do it a better way anyway. So what we're going to do is the following. What if I went from, let's say, this position to the next position right there and calculated the work in that short little step? During that step, it's pretty much a straight path, right? So during that step, I can use my normal work calculation. I can say the work is F dot delta R. So the force is mg and delta R is some direction. I don't really care. It's just from here to there, whatever that is. And then I could do the next little step, and then the next step, and the next step, and the next step. I can add up all those works done until I get down to here. Notice that there is an angle between there. I don't really need to know what that is. But since there's an angle between there, it's not going to be equal to the gravitational force times half of the circumference, because there's an angle in there that does matter. I'm not going to calculate the cosine of theta. Well, kind of I am. So what I'm going to do is, once I find the work during that little segment, dw F dot delta R, then I'm just going to add up all those works along that whole path, and I'll get the work done by gravity. And then I can compare that to mg delta y, the gravitational potential energy, which is, y2 minus y1, like that. Okay, let's do this. I've already kind of started. So here's what I have. So I made a ball, and I made the ground and everything like that. Let's just run this and see what it looks like. I want to visualize what's going on. So there's my ball, and I want to move it. I don't want to calculate work. I want to just move it down here. So that's the first thing I'm going to do. So I've already said this angle. I should have drawn a picture. Well, you can see right here. Suppose that I have, here is the center, and I draw a line going up here. If I am at any other position, this angle, I could use this angle theta to calculate where it is. And I should have gone into the details of this, but I'm not going to. So let's say while theta is less than or equal to pi, then I need to do a rate, because I'm actually, the rate thing says how fast to make these calculations move. So what I need to do is move the ball. So I'm going to say ball.pos equals center. So I have this center thing up here because I didn't want to put everything at the origin. Center, which is just a vector, plus r, big R, times vector sine theta, cosine theta, 0. And so here I have my r value. I have my theta is 0. Omega is just how fast I'm changing that. And then so let's actually do that. I do need to increase theta. So I can say theta is theta plus omega times dt, which I got rid of. dt equals 0.01, which is just a dumb way of saying it. I could have said d theta. Okay, let's save that and see if it works. Check that out. Circular path. Perfect. And I have a ground there just for effect. Okay, we have to check things, right? So is this path length equal to half of the circumference? So let's say this. Let's say s equals 0. And then I'm going to go up here and say old equals ball.pos. So this is a vector location for the ball before I change it. And I'm going to change it. So now I have a change in position. So now I can say dr equals the final position, which is going to be ball.pos, minus initial position, ball old, which is just a vector. So this is the change in position going from one dr to the next. Now what do? Well, now I'm just going to find the length of that piece and add it to my s. S is my total arc length. So I can say s equals s plus the magnitude of dr. I can't add it to dr to that because that's a vector, and s is a scalar. So as I go around, this should add up, and I should get pi times r. So let's find out. Let's say path equals s, and I'll leave the units off. And then let's also print half c equals pi times r. Let's see if those two give the same thing. I'm kind of nervous. Check that out. Okay, they're not the same, right? 6.2799, 6.28. And I think you could figure out why. If I increase this, and let's just pump that up because I want to go fast. Check that out. So that's as good as you can get, okay? But I'm going to put it back to the 0.01 just because I want to. Okay, so I don't need to print that out anymore. Now I need to calculate the work. I feel like that is a half a circle, so I'm comfortable with that. So now we're going to calculate the work. So let's say the work is 0. Now I need to come down here and calculate d work. It's going to be equal to F, which is going to be m times g, and I do have g up here. Yep. Oh, no, I'm doing the dot product. The dot product is built into Python. Dot m times g dr. So that's all I do, f dot dr. That's it. And then just work equals work plus d work plus d work. And then let's just print that out. And I'll put the units because joules. And then let's print out, let's calculate it. I'm trying to say, okay, let's just say y1 equals, it starts at, y1 is at 3 up here, and then y2 is at, let's see, so this is a radius of 2, what's this? -1. Yeah, I don't know why I picked these values. I just did. Yeah, that's weird. Okay, so du, the change in potential, is going to be m times g, mag g, because I have to use a vector, times y2 minus y1. I'm doing it the full way because, you know, and then let's print that. Joules. Error. Oh. That was an easy one to fix. Check that out. The work done by gravity is positive because it's essentially moving in the same direction as the gravitational force. I'm not sure why that did that. I think this because my theta's rate's too high. And the change in gravitational potential energy is negative, but the same magnitude, right? So this works. I claim that this works. I'm super pumped up. I'm going to change this down right here. Let's rerun that real quick. Make sure that it's not doing something crazy. Yeah, okay, it is. It's fine. And I'll save that. I'll give you the link to this code down below. But I feel confident that I'm justified in saying that the path for the gravitational force, the work done by gravitational force, is not path independent, is not path dependent. It does not matter about the path. So you can use the gravitational potential energy. This is true for our constant gravitational force we have right here. We can do real gravity, the 1 over r squared gravity later. It's going to be great. Okay, subscribe, check it out. See you later. There's going to be a ton of work videos. It's going to be great. I'll talk to you guys later.